In today's video, we are going to carefully explore the concepts of activity and half-life and examine how both of these can be calculated accurately and understood properly in various scientific contexts. We have already discussed that certain materials contain unstable isotopes and that in order to achieve a more stable state, these isotopes undergo decay by releasing some form of radiation, which could be in the form of an alpha particle, a beta particle, or gamma rays. Materials that exhibit this behavior are referred to as radioactive materials, and they exist in many different forms across a wide range of substances. Now, if we take a moment to consider just a single radioactive isotope, we will find that there is no reliable method to determine exactly when it will decay, because the process of radioactive decay is entirely random and unpredictable on an individual level. However, when we look at a large enough quantity or sample of these isotopes, the randomness averages out in a way that allows us to determine two very important and helpful measurements. The first of these is known as the activity of the sample, which refers to the overall rate at which decay is occurring within all the isotopes present in that particular sample, and this activity is measured in a unit called becquerels, where 1 becquerel represents 1 decay happening every second. For instance, if a sample has an activity of 600 becquerels, it means there are 600 radioactive atoms undergoing decay every single second within that sample. The second crucial concept is half-life, which can actually be defined in two different but equally valid ways. It can either mean the amount of time it takes for half of the radioactive nuclei in a sample to decay, for example going from 1 million unstable nuclei down to 500,000, or it can refer to the time it takes for the activity, or number of decays per second, to be reduced by half, such as dropping from 600 decays per second to 300 decays per second. To better visualize and understand this, let us consider a simplified scenario where our radioactive sample consists of 100 unstable isotopes, each capable of emitting radiation to reach a stable state. When we observe the sample over time, the first thing we notice is that the decay process is entirely random, meaning there is no possible way to determine when any specific isotope will decay. However, as more and more isotopes undergo decay with time, the total number of unstable isotopes that are left gradually decreases. As this number goes down, it naturally causes the activity of the sample, that is, the overall rate of decay, to also reduce. This is exactly why the decay of a sample appears to slow down over time, even though the decay process itself remains random and unchanged. This understanding leads us to the clear conclusion that half-life can be used to describe either the time it takes for the number of remaining radioactive nuclei to be reduced by half, or the time it takes for the activity to decrease by 50%, and both of these interpretations are directly connected since fewer radioactive atoms will always result in a lower activity. Another very useful way of demonstrating this decay process is by using a graph where we plot the activity measured in becquerels on the vertical axis and time on the horizontal axis. As we move forward in time, both the number of radioactive particles and the activity will continuously decline. However, this decline does not happen at a constant rate. Instead, it slows down gradually, which is why the line on the graph is curved rather than straight. To calculate the half-life using this type of graph, we need to find the time duration during which the activity is reduced by half. For example, if the activity starts at 600 becquerels and drops to 300, we observe that this change takes approximately 2 hours. To confirm this result, we can further check how long it takes to reduce from 300 to 150 becquerels, and if that also takes about 2 hours, we can be reasonably certain that the half-life of the sample is 2 hours. If we consider a different radioactive sample, one that decays more rapidly, we would see a graph where the activity starts at a much higher value and decreases very quickly, indicating a much shorter half-life. In this case, possibly 1 hour. Up to now, we have assumed that the activity value is known to us, but in real-life situations we have to measure it using an instrument known as a Geiger-Müller tube and counter. These devices detect all the radioactive decays that reach them per second, including alpha particles, beta particles, and gamma rays, and they report this information as a count rate. It is this count rate that we typically use to estimate the activity of the sample in question. Now, before we end the video, let's go through a quick practice problem. Suppose the half-life of a radioactive substance is 40 hours, and we start with a sample containing 3 million radioactive nuclei. We are asked to determine how many of those nuclei will remain after a total of 5 days. First, we convert 5 days into hours by multiplying 5 by 24, giving us 120 hours. Next, we divide 120 by 40, the half-life, and find that the sample has undergone 3 half-lives. To calculate the final number of nuclei, we simply have 3 million 3 times. First halving gives 1.5 million, halving that gives 750,000, and halving once more results in 375,000, which is the final answer. That wraps up everything for today's video, and I hope you found this explanation helpful and informative. I look forward to seeing you in the next one very soon.